Hello, I hope you can hear me. Uh, this is the assignment solution session for week 10, and today we have the following questions. So the first question is, which of the following is true if a system has both inversion as well as time reversal symmetry? Now, when a system has both inversion and time reversal symmetry, then the system can be said as fully symmetric. Symmetric where the system, let's say the potentials preserve the time reversal symmetry. V of minus r becomes stays at this, and time reversal symmetry as well. Let's say we have some operator t, a time reversal operator operating on psi still gives us the same values as E psi. So in such conditions of a full all the symmetric operators, we also have symmetry in eigen values also, and the full set of eigen vectors would be, in the case of given options, as E of k up will equal to be E of k down, and E of minus of wave vector up for the up spin will be E of minus k vector down. Now for a fully symmetric constraints in the system, the system is both inversion as time reversal, so we also have a full symmetric set of eigenvalues. So this following option would be true for a system having both inversion as well as time reversal symmetry. Now with spin orbit coupling in a p band, now a p band one knows has 6 states to it, and in the presence of spin orbit coupling, this all the 6 degeneracy is lifted and p band splits into 2 of the bands. Let's say for a p band L is equal to 1, and let's assume that it has 1 electron, so S will be 1/2. So we can have values of J to be half and 3/2. So in such a case, when we have spin orbit coupling, so we will be having 2 states with angular momenta J is equal to half and J is equal to 3/2. So the correct option would be 2 states with total angular momenta J is equal to half and J is equal to minus half. Now question number 3 focuses on the thing that consider a p band in a cubic crystal with side A. So the correct options we have to choose now. All the 3 p bands are degenerate only at kx, ky, kz, k equal to 0. That is one statement. All the 3 p bands are degenerate at kx, ky, kz equal to pi by 2a. All the 3 p bands are degenerate at this, and all the 3 bands degenerate over the entire Bitcoin zone. Now in case of p bands, we know that if we draw ek diagram for p bands, we know that all these, let's say this is k is equal to 0, and p bands are degenerate only at k equal to 0. So one can draw 6 p bands going from, let's say this is a gamma point, and we have other high symmetry points as well. So the degeneracy of these p bands, that is the value of similar value of energy, is only possible at gamma point. So gamma point is nothing but kx, ky, kz equal to 0. So the correct option would be all the 3 p bands are degenerate only at gamma point over kx, ky, kz equal to 0. Now question number 4 relates to Rashba Hamiltonian. The expression for Rashba Hamiltonian for a 2-dimensional thin film in the xy plane is. Now Rashba Hamiltonian for 2-dimensional thin film can be written as minus alpha r, which is Rashba constant, sigma npr spin and orbital momentum, dot product taken in z direction. Now sigma, this cross product of sigma cross P can be easily written down as follows, that sigma x, sigma y, sigma z, px, py, pz. This cross product is taken as a dot product with z cap. Now when we are taking dot product with z, the other x and y component are 0, so only z component will survive after taking this dot product with z. So we will only consider the k component, and the k component is nothing but sigma x py minus sigma y px. So this is the dot product of this whole term, and we are left with Rashba Hamiltonian to be minus alpha r sigma x py minus sigma y px, which is nothing but option number A. Now for a single band, if the Rashba constant alpha r is calculated from spin orbit interaction and measured experimentally, then which of the following is correct? Now Rashba this constant in the Hamiltonian, Rashba constant, can be written as alpha r is equal to minus g Bohr magneton h cross divided by 2 mc square times the electric field. Now this Rashba constant is controlled by the applied electric field. So if one applies some huge amount of electric field, this Rashba constant can be observed. But the problematic thing in the denominator is mc square, which is very large for an electron, because C is very large and the approximated value is in million electron volts. This makes the effective value of alpha r to be very small, but still it is observed in experiment simply because in real materials there is an overlap of S bands with higher lying P bands, which in effective generates a band gap in the system and decreases the denominator. So the experimentally found values of alpha r are in general greater than the theoretical one or calculated ones. So experimental values are larger than the calculated ones. Now the next question is for the inverse participation ratio. Now to understand inverse participation ratio, one can look into the participation ratio. Which means that participation ratio, or people call it PR, it calculates the participation of all atoms in the unit cell to the vibrations of a given phonon mode. So this participation ratio is more discussed in context of thermoelectrics, where everyone, or we are more concerned with traveling of energy or traveling of heat. Heat is nothing but phonons. So in general, this participation ratio is approximately 1 for a perfectly crystalline solid, because all the atoms are very strongly bonded to each other, and therefore all atoms are participating in transporting phonons. But this participation ratio can vary between 0.5 to 0.6 for amorphous solids. So let me take a separate page. So this participation ratio, only PR I'm stressing on, is defined as the following expression. I goes from 1 to n is the total number of atoms in the cell. Divided by the denominator, there is a term m of I, which is the mass of the ith atom. I'll define it in a bit, divided by m of I square. So take a different color. E of iq, E of I omega q, is the eigenvector for the phonon mode at a wave vector q for frequency omega q, and m of I is mass of ith atom in the cell. So this participation ratio tells that how much percentage of the atoms are actually participating in transporting heat from one part to the other, and as I've already mentioned that it is extremely important in the field of thermoelectrics. Now in the same context, inverse participation ratio, IPR, inverse is nothing but we can define it as follows. It would be almost an inverse of the participation ratio, where we have the fourth power in the numerator I CIK square. Now this goes by the same token that if one takes an inverse let me just check it. I think I missed a power of, yeah, I missed a square power. Sorry. Okay, so inverse participation ratio is nothing but the is reciprocal of the participation ratio in the context of when maintained in the same context, where CIKs are the coefficients of the orbitals which are participating in the overlap. So the correct option for now CIKs are the coefficients of the orbitals, and the correct option would be option number B. Oh, sorry. Wait a second. Sorry. The fourth power is in the numerator. So correct option to the inverse participation ratio would be IK sigma I. Yes.
Yes, it will be A.
Yeah. So it will be 4 powers in the numerator and square of square in the denominator. So next question is again concerned with the inverse participation ratio, that if a state is fully localized for a d-dimensional system of size L, then inverse participation ratio is. Now if a state is fully localized, then as we saw above, that psi k, which is I'll just write here, psi k, which is nothing but the summation of CIKs and phi I. So if a state is localized, then all the coefficients will die out. Let's say ith, we are talking about the ith state, and electron is present at some ith atom. So ith state is the one where electron is present, and all the other coefficients will die out, will be 0. So in that case, inverse participation ratio IPR would be CIK raised to power 4 summation CIK raised to power 4. Here, let's try it again. Divided by summation CIK mod square. Now all the CIKs, if 0, then numerator and denominator would have only one CIK, which raised to the power 4, and denominator and also raised to the power 4 would be 1. So in the case of fully localized system, we will be having IK, which is close to 1. Now in the same context, for an extended state of d-dimensional system of size L, this inverse participation ratio boils down to an empirical relation of IK similar to 1 divided by L is the size of the system and D is the dimensionality. So it goes as 1 divided by L raised to the power D, which is 4th option in the present assignment. Then the 9th question says that which of the following statements is correct in the case of direct bandgap semiconductors. Now as we know that semiconductors are of two types, direct bandgap and indirect bandgap. Direct bandgap are those where transition occur from the same K value from the maxima of the valence band to the minimum of the conduction band. Now let's say we are at some particular K value, and for the time being let us assume that it is 0. And if one draws the EK diagram for a direct bandgap semiconductor, then transition occurring from valence band to conduction band are vertical transitions. So occurring from same K value to other K value, it can also occur from other points as well. So for direct bandgap, semiconductors, the maxima of the valence band, or VBM, that transition will occur from valence band maxima to conduction band minima at the same K value. And the following option is B, that the maxima of the valence band and minima of conduction band occur at same K values. Now question number 10th is with if the reduced mass of an electron hole pair, mu is the reduced mass of electron hole pair, and the epsilon given is the dielectric constant of the material in which this exciton is present, or this electron hole pair is present, and small m is electron mass. Then we know that the following expression holds, that the exciton radius, if I say that if A is the exciton radius, then exciton radius for this, let me call it Ex, is equal to epsilon times mass of electron divided by the reduced mass times Bohr radius. A of H is the Bohr radius. So we can arrange this thing, dielectric constant m by b. So the ratio of this mode Vanier exciton to the hydrogen atom Bohr radius is given by epsilon times mass of electron divided by u, which is the option number A. Now question number 11 is the following, that which of the following statement is true for H and J aggregates related to an isolated molecules. Now these H and J aggregates, these relate to organic semiconductors. Now let me draw two pictures to explain this thing. Now if EK diagrams, if let's say we have a material in which the behavior of EK diagrams is as follows, that there is a minima at k equal to 0 and it behaves, and other material in which EK diagrams has a maxima at this value, let's say k equal to 0 again. Now if we excite this system, let's say I excite this system to this energy, giving E1 initial energy, then thermalization will occur and the system will come down to a lower energy state, and a vertical transition will occur with lower energy, let's say E2. So E2 is less than E1, but since this transition is allowed, as it conserves momentum, because this is a vertical transition occurring. So in a vertical transition, k final, that is a wave vector at the final stage, minus k initial is 0. So it is conserved via momentum as well as energy, because this all the thermalization means non-radiative processes, and system will relax via non-radiative processes, and finally E2, that is energy of emission, will be there. But in case of systems where such kind of diagrams occur, such kind of behavior of energy versus k occur, let's say we excite the system to this place, a vertical transition giving energy E1. Now in general, let's say if this is the Brillouin zone, write it pi by A and plus of pi by A, the system if goes down to lower in energy, let's say this separate color, this point is A point. In general, these are not high symmetry points, I'm just labeling as initial and final points, B point and C point. So system goes from A to B, and via thermalization system goes from B to C. Now to come to the initial state, there has to be a slant transition, which for sure will not conserve the momentum, because kf minus now ki will not be equal to 0. So this momentum is not conserved in this transition. Rather, if by some other external processes, if the system can take energy, let's say from collisions via other molecules or some external agents, and if B reaches the or let me call it this transition to yeah, the initial state would be this. Let me just this C would be the 0, because system would relax down to the ground state, and ground state is 0. Okay, now in this case, when system gains energy from external agencies, now it can relax as a vertical transition straight to the ground state. Now this energy of emission, let's say E2, now in this case E2 is greater than E1, but since the system does not conserve momentum, or yeah, just a second, let me just give a minute in the explanation if I'm missing something. Yeah, no, okay, that's fine. E2 would be greater than E1, and in this case E2 was less than E1. So this kind of system where E2 is less than E1, these are called J-type aggregates, and in these systems, these kind of systems are called H-type aggregates. So in an H-type aggregate, energy shifts to blue side of the spectrum, whereas in a J-type aggregate, energy shifts to red side of the spectrum, but the emission is intense, and in the case of blue, emission is faint. So the correct option would be J-type aggregate has J aggregate has red shift and in the absorption, and the emission is intense. Now the next question, which is according to Kasha's rule. Kasha's rule is nothing but the fundamental process that occurs in system. That is, if we have multiple excited states in a system, let's say if I draw the configurational coordinate where this E equals to energy and this is the nuclear coordinate, and if I draw, let's say this is the ground state energy of the system, and this is the equilibrium distance, let me call it R0, and this is first electronic surface or electronic state. This electronic state will have vibrational states in it. Now a higher excited state would have a larger equilibrium distance associated with it, as in excited states things vibrate vigorously and with large amplitude. So this is an excited state, excited electronic state, and let me call it ground electronic state. Now in the nomenclature this is called S1, and it can be S0 or it can be S1 or S2 or S3, and let's say there are other states as well present, other excited states present as well. Now the Kasha's rule says that now we can excite the system from, let's say, the ground state to any other higher state available depending upon the initial energy, and the system can relax via processes called internal conversion or intersystem crossing, but the emission will be occurring from the lowest available electronic state in the system, which in case is this one, which in this case is this, that is S1 to S0. So fluorescence basically occurs from same state, that if it is singlet from S1 to S0, or if it is triplet, then T1 to S0 would be phosphorescence, which will be a delayed, nothing but delayed fluorescence. So fluorescence what occurs from S1 to S0, and this transition rule is nothing but Kasha's rule. So S1 to S0, that is transition from the lowest first excited singlet state to the ground singlet state, is nothing but fluorescence, and option is S1 to S0. Now question number 13 again discusses inverse participation ratio, as we have already found that for in case of extended state of the system, IPR can be written down as 1 divided by the size of the system raised to the power of dimensionality. Now in case of a three-dimensional solid, it will go as 1 divided by LQ, and following is the option. Okay, so this so we have completed the assignment. If there are any questions.
Question number 2, please.
Yeah. Okay, this one.
Okay, I have mistaken.
Okay.
Actually, in the current assignment and assignment 11, I feel that question number 1 and question number 13, both of them the right answer is, the option that I felt right was typographically errored or something. What can I do? What should I do
In
to report
assignment 10 or 11? 11.
11. Uh,
um Now that would be a
because
bit difficult one to say for me.
tomorrow is the last date, so I'm asking you, whom to inform.
Okay. Okay. So yeah, I'll ask the professor to have a look into
I
this.
will look. Okay. Thank you.
Okay.
Assignment 11 or question number 1 and 13. First
One.
and last question.
Okay. All right. I have noted.
Okay. So can you communicate within tomorrow 12 at the last date, last time there is a deadline to submit.
Sure.
So please.
Sure. Sure.
Okay.
I'll do all the what I do. I'll write a
Mhm.
mail to the professor,
Okay.
and let you know.
Hmm.
Okay.
Question number 1 and 13, assignment 11.
All right. Okay.
Okay.
If possible, you can drop me an email.
Oh, your mail address.
Okay. I'll write in the chat box. You can note it down from there.
Okay.
Okay. Okay. So with this, I think we can close today's session. Hello.
Yes.
Okay.
Okay.
Thank you.